Hi, in this video we'll be talking about stereochemistry. So many molecules and objects have chirality. So chirality is also known as a handedness and actually comes from the Greek word for hand. And another way of thinking about that is it has a non-superimposable mirror image. And let's dig into that a little bit deeper. So if you have a face, and you look at that face that's perfectly symmetrical in a mirror, you would see that these two faces, you could grab one of them and put it directly onto the other one, and they would be perfectly superimposable. But let's say that face had a blemish. Well, in the mirror, that blemish might be on the left side of my face, but in the mirror, it would actually appear to be on the right side of that mirror imaged person's face, and those two faces are no longer superimposable. That is to say, I couldn't grab this face and drag it over onto this other face and have the two perfectly line up. So molecules also have the ability to have a mirror image, and so let's look at isopropanol in a mirror. And so isopropanol, if it were to see itself in the mirror, would see isopropanol, and this isopropanol on the right is perfectly superimposable with the image on the left. So isopropanol is not chiral, or you could say it's achiral. But if you simply add one more carbon to that, you now have 2-butanol, and 2-butanol, if you were to look at 2-butanol in the mirror, it would see itself in this way. The way you can think about these is this first carbon is closest to the mirror, therefore this carbon is closest to the mirror, this carbon is second closest to the mirror, second carbon is second closest to the mirror, and that's one of the ways you can evaluate these mirror images. So let's take these two and see if they're superimposable. And this is sometimes where a model comes in handy. If you were to flip this molecule over, this alcohol functional group, this hydroxyl, would go from coming out of the mirror at you to going into the board, or coming away from you. And you can see very clearly that these two molecules are not superimposable. One is going out and one is going back. That means that these images are non-superimposable, which means that these two molecules are indeed enantiomers of each other. And an enantiomer is simply another type of isomer. So how do we differentiate when we're looking at the two enantiomers? How can we tell which enantiomer is which? We don't want to say the coming out of you enantiomer because it depends on what direction you're looking at it from. So we need a way to differentiate these. And we need to prioritize. And that's the key first step in figuring out which enantiomer is which. So the way that the convention is, once you've prioritized 1 through 4, where 4 is the lowest priority, we put 4 in back, as if it's part of a steering column. I'll have another way of showing you how to do this in class using your hand, but we'll save that for class. So a steering column, for those who are not familiar, is the part of your car that connects your steering wheel to the rest of your car. And so now 1, 2, and 3 are effectively oriented like a steering wheel. And the direction in which you are steering when you're going from 1 to 2 to 3 is the direction of, and that's how we differentiate this chirality. So in this case, we're going from 1 to 2 to 3, we would be taking a left-hand turn, and lefties, as we all know, are sinister, or at least they are in the ancient Latin. That's where the word sinister comes from. And so we call this left-handed turn enantiomer the S enantiomer. Let's look at the enantiomer of S. And so, as we saw before, this orientation is S, and the mirror image of that is shown right here. And let's set up the priorities, again, 1, 2, 3, 4. Put 4 in the back as the steering column, and let's steer from 1 to 2 to 3. And so if we did that, we would be taking a right-handed turn, and we call that R. The R is actually not for right, it's for rectus, but you can think about R for right. So now that we know how to differentiate S and R, we need to look at how to prioritize atoms. And this turns out to be one of the easier things in organic chemistry, thankfully. The very simple rule is that heavier elements have a higher priority. So that is to say, hydrogen is pretty much the lowest priority on the periodic table. Carbon's bigger, so it has a higher priority. Oxygen's bigger, has a higher priority. Aluminum, even though it's down to the left of oxygen, is bigger and it has a higher priority. Bromine also has a higher priority. So you look to the atomic number, and the higher number has a higher priority. It does become a little bit challenging when you're trying to look at slightly larger molecules. So if we looked at 2-butanol, as we were looking at before, you look at the stereogenic center. So stereogenic means it has the ability to create a stereo center, and chiral molecules often have stereogenic centers. They don't have to, but most do, especially in sophomore organic chemistry. So if we look to this red dot, that is the carbon that is the stereogenic carbon, and we look to what's bound to it, there's an oxygen, a hydrogen, and there are 2 carbons. And so the oxygen and hydrogen are really easy to figure out as the priorities being 4. Hydrogen has the lowest priority, it almost always does. Oxygen has a higher priority than carbon because it's a heavier element. And now we're looking at the 2 different carbons on the left and the right. And on the left, you have a carbon that is bound to 3 hydrogen atoms. And on the right, you have a carbon that's bound to 2 hydrogen atoms and another carbon. So that extra carbon now gives it priority because carbon has priority over hydrogen. So you kind of go out in concentric rings, kind of like an onion moving out away from the center. Let's look at a slightly larger molecule here, and we'll look at the stereogenic center. The first challenge of any question of chirality or R and S is actually to identify the stereogenic carbon. So that stereogenic carbon happens to be the one that is bound to the nitrogen. And so that carbon is bound to a nitrogen, a hydrogen, and 2 carbon atoms. So far, as stated, it is not stereogenic because there are 2 of the same group. So we're going to have to move one further ring to see what those carbon atoms are bound to. Again, the 1 and the 4 are easy, but now let's differentiate between these 2 carbon atoms. In one case, you have an oxygen atom, in the other case, you have a carbon atom. Well, oxygen has a higher priority than carbon, and therefore the number 2 is on the left, and the number 3 is on the right. So this is a common error that is made because people will be tempted to see, oh, look, all these other atoms here, this has a lot higher mass on it. But that they're not taking into account that the way that this nomenclature works is you work 1 atom at a time. You keep moving ring by ring by ring. You don't look at the whole thing. You, again, go 1 atom at a time. And that's all we have for today. Have a good rest of your day.